9.1 Collinear and perpendicular vector addition. A vector is a physical measurement. With magnitude, which is another way of saying the number that goes with the vector, or the amount, and direction. We can represent vectors in diagram form by drawing arrows. These arrows are drawn so that they're pointing in the same direction as the vector, and the length of the arrow should show about how large the magnitude of the vector is relative to other vectors. Now, we're not going to get out a ruler to draw the arrow to make it exactly the right length, but we should draw it so that vectors that have larger magnitude are longer than vectors with smaller magnitude. For example, the vector 15 meters east has a magnitude of 15. And a direction that is east. We can draw this vector by drawing an arrow that is pointing east and labeling it 15 meters. Now, if another vector was to be drawn that was 10 meters west, it needs to be shorter than the 15-meter vector because 10 is smaller than 15. And 5 meters south would point south and be shorter still because 5 is shorter than 10. We're going to start with collinear vector addition. You're already pretty familiar with collinear vector addition from your 1D motion study, which is why it's a good place to start. Vectors are collinear if they point along the same straight line. Remember from your study of math that the word linear means straight line. Vectors are collinear if they're both pointing along the same straight line. This means that they're pointing the same way or opposite. For example, here's 3 vectors, vector A, vector B, and vector C. Since they're all pointing along the same line, vectors A, B, and C are collinear. Same is true if we draw them like this. Even though they're different lengths and sometimes pointing the opposite direction, they're still pointing along the same general line, which is why they're collinear. To find the sum of collinear vectors, you must add their magnitude if they point the same direction, and subtract if they point in the opposite direction. For example, the vector 10 meters east plus 15 meters east. These are collinear vectors because they're both pointing along the east line. We draw a diagram to help us with our vector addition. This type of vector diagram is called a tail-to-tip vector diagram, and we use tail-to-tip vector addition. That means the tail of one vector touches the tip of the other and they're lined up. It also means that the answer goes from the tail of the first vector to the tip of the last. This answer is called the resultant in vector addition. And this resultant is 10 plus 15 is 25 meters to the east. The resultant vector, or the answer, is drawn from the tail of the first vector to the tip of the last. This is why we call it tail-to-tip vector addition, because it tells us how our answer is drawn. Example: 10 meters east plus 15 meters to the west. These two vectors are also collinear because east and west point along the same line. In this case, the diagram draws the tail of the second vector next to the tip of the first so that they're lined up. The resultant vector travels from the tail of the first vector to the tip of the last. And we can see that this vector is going to be shorter than either of the two vectors because it's made up of a subtracted vector addition. To find the answer, since these vectors are going opposite ways, we subtract their magnitude and get minus 5. This means that the resultant is 5 meters. Negative tells us it's west. The second type of vector addition we're going to look at is perpendicular vector addition. Perpendicular vectors are vectors that are 90 degrees to each other. The resultant for perpendicular vector addition has a magnitude and a direction like you're familiar with, but there's also another piece that's new. The direction can't be one of the many directions we have because it's made up of a combination of directions. So the direction is at an angle, and this angle is a combination of the directions of the two original vectors. Here's a general method for how to add two perpendicular vectors. If we add the vectors a plus b, and the resultant is vector c, a and b are our original vectors, and c is the resultant. The resultant vector c is going to be written in this form, where the first piece is the magnitude. That's the number that tells us how much c is. Theta is the angle that the vector is at, and this last piece we're going to call the of statement. It tells us the combination of directions that the vector is at. We'll start by drawing a diagram, tail to tip, that shows the combination of vectors A and B. The resultant vector goes from the tail of A to the tip of B. Now, we know that the angle between A and B is 90 degrees, but there's still two unknown angles in this triangle. We're going to call theta 1 and theta 2. First, to find the magnitude of the resultant vector, we use Pythagoras' theorem, which is a squared plus b squared equals c squared. This means that the magnitude of the resultant, c, is the square root of a squared plus b squared. To get the angle, we need to use trigonometry. Either theta 1 or theta 2 are accurate answers that we could give for the angle for the vector c. However, you need to make sure that your theta 1 and your theta 2 match the of statement that follows them. To find these angles, we use tan theta equals opposite over adjacent. For example, to find theta 1, we use tan negative 1, where the opposite to theta 1 is b and the adjacent is a. To find theta 2, it's the opposite, tan negative 1, a over b. To complete the of statement, we need to examine the combination of directions that create vectors A and B. We'll start by looking at the navigational grid so you can understand what the of statement actually means. The directions we were working with on Earth are north, east, south, and west. A vector pointing into the northeast quadrant can be either called north of east or east of north. It depends on which side of the vector you're looking at. That's why every vector has two angles that could describe it. A vector in the southeast quadrant could be described by an angle that is south of east or an angle that is east of south. Either of these angles is correct, it's just two different ways of getting to the same vector. An angle in the southwest quadrant could either be south of west or west of south. And an angle in the northwest quadrant is either north of west or west of north. To create our of statement, we go back and look at the tan function that we used to get our angle. We use tan negative 1, something on the top, divided by something of the bottom. And this gave us one of our two angles. Our of statement is going to look like angle blank of blank, where the first box takes the direction of the top vector, and the second takes the direction of the bottom vector. Here's an actual example. 25 meters to the north plus 17 meters to the west. These perpendicular vectors are drawn like this, so that the tail of one matches the tip of the other, and the resultant travels from tail to tip. The magnitude of the resultant comes from Pythagorean theorem, 17 squared plus 25 squared, square rooted, is 30. The angle, and we can choose to either go 25 over 17 or 17 over 25. For this example, I'm going to go 17 to the west divided by 25 to the north. Tan negative 1 of this gives us an angle of 34 degrees. To construct our of statement, we notice that west is on the top and north is on the bottom. And our of statement is always top of bottom. Which is west of north. This means that the resultant of 25 meters north plus 17 meters west is 30 meters at 34 degrees west of north. Another example, and this one isn't going to use our standard compass directions. 15 meters to the right plus 37 meters up. We start by drawing our tail to tip diagram, showing our vector triangle. The magnitude of the resultant is 15 meters squared plus 37 meters squared, square rooted, which is 40. And the angle is tan negative 1, 37 up, divided by 15 right. This is 56 degrees. And the of statement is up of right. Now that sounds a little bit weird, so we might convert that into English before we write out our answer to just saying above the right vector, or above right. This gives us a resultant equal to 40 meters at an angle of 56 degrees above right.